Hello dear students, good evening. Today we are going to start our new unit titled Linear Programming Problems. This is the first session. Now before I proceed further, could you please confirm that you are able to view the screen properly and able to hear my voice very clearly?
Yes, sir.
Okay, alright. So linear programming problems. Okay, so if you see here, there is a term called a linear. Okay, and then there is just a minute. What happened to my digital board? Let me make my digital board fix. So as you see, there is a term called linear. Then we will also see that why the name programming is there, and obviously it is related to some problem. That's why it is linear programming problems. Okay. Now let us understand the significance of why it is a linear programming problem. Let me go to the next slide of my class note, and then I will explain. So dear students, to give you a background is that earlier classes, that means earlier classes I wanted to mean is that in previous year, last year, we have discussed system of linear equations. Okay. You know what is system of linear equations, and we have also solved problems or related to the application of linear equations in day-to-day problems. In the last year, when we are in class 11, we have studied linear inequalities and system of linear inequalities in two variables and their solution by graphical method. Why I am saying so, dear students? Because these two are the prerequisite, that is the system of linear equations and solution to the system of linear inequations in two variables using graphical methods. So these two information are required to this topic, linear programming problem. So many applications in mathematics involves system of inequalities or inequations. Okay. In this chapter, we shall apply the system of linear inequalities, okay, linear inequations to solve some real life problems of the type as given below. Let us first take this problem, and based on this problem only we will complete our entire discussion today. Okay. What is the problem? The problem is mentioned here. A furniture dealer deals in two items, tables and chairs. Okay. He has rupees 50,000 to invest and has storage space of at most 60 pieces. So there are two constraints here. First constraint is that the furniture dealer is having 50,000 rupees to invest. He cannot invest more than that. So that is one constraint. And where here he is going to keep all the tables and chairs, that's the space has a constraint to accommodate at most 60 pieces including tables and chairs. So these are the two constraints. Now a table cost rupees 2,500. A table cost rupees 2,500 and a chair cost rupees 500. So now that is the cost price. Now he estimates that from the sale of one table he can make a profit of rupees 250, and that from the sale of one chair the profit is rupees 75 per selling of a chair. So now if this is the problem statement, what will be the objective of the furniture dealer? Obviously the objective of the furniture dealer is to sell that many tables and that many chairs which will give him maximum profit, obviously. So he wants to know how many tables and chairs he should buy from the available money so as to maximize his total profit, assuming that he can sell all the items which he buys. Correct? Whatever the items he buys, okay, all the items actually getting sold, and by means of this entire exercise, what is the number of tables and chairs should be, so that the profit earning is maximum. That is the problem statement. And as I said few minutes back, in today whatever the discussion we will go through, we will take this example and proceed further. So this type of problem is actually linear programming problem. Before proceeding with linear programming problem, let us understand what is about the optimization. So this is and what is the optimization, and after that we will come to the linear programming problem. So let me go to the next slide of my class note. Now the problem what I just mentioned, such type of problems which seek to maximize profit or minimize cost. In the example what I gave, that is deal with maximize profit, but for some other type of problem it can be minimize the cost. Okay. So whatever the problem statement is, that the end objective is either to find maximum or to find minimum. In case of profit, it is a maximum profit. Profit should be always, our target will be profit to make profit maximum, correct? And whenever there is a cost, our target should be to minimize the cost. So whether it is maximize or minimize, in one statement we say it is an optimization problem. Okay, in one statement we can say it is an optimization problem. Thus, an optimization problem may involve finding maximum profit or minimum cost, or it could be minimum use of resources. When we want to achieve some result by using the resources, our target will be how we can achieve the result using minimum number of resources, and also we want to see that how we can get the result, impact of the result will be maximum. So these are the all optimization problems. A special but a very important class of optimization problem are linear programming problem, and in short it is known as LPP, linear programming problem. Whatever the problem I have mentioned earlier about the that furniture dealer purchasing chair, tables and then selling it, that problem is an linear programming problem. So linear programming problem are of much interest. Why? Because of their wide applicability in industry, commerce and management sciences. So for example, whatever the problem statement I just mentioned, that is a very interesting problem. If we keep ourselves in the position of a furniture dealer, our target will be always to think in that way, that how to maximize the profit. Okay, subject to all those constraints. What are the constraints? First constant was 50,000 rupees is the maximum he can invest, and there is a constraint on the space where he can keep maximum of 60 items including both chairs and tables. So in this chapter we will study some linear programming problems and their solution by graphical method only. Okay, apart from graphical method, there are many other methods available to solve linear programming problem, but we will only stick to graphical method only. Okay, so let me now proceed further to explain. at any point of time, if you have any doubt, never hesitate to ask me. Okay. So, the problem statement, let me mention once more, because it is important that you also note down this problem, and because based on this problem statement will be the discussion will be more meaningful. Okay. I am not reading that problem statement again, because this I have already read. You just, it is for your reference. Now, in this problem, we observe the following two things. The first one, the dealer can invest his money in buying tables or chairs or combination of thereof. That means he can buy all the, he can use the entire 50,000 money to purchase only tables, or using that 50,000 rupees to purchase only chairs, or a combination of chairs and tables, means few chairs, few tables, so that after purchasing the cost, the entire the cost become 50,000 rupees. Okay. So, further he would earn different profits by following different investment strategies. So, if he purchased all the chairs, the profit will be something different. If he purchased all the tables, the profit will be something different. If he make use of some combinations of chairs and tables, profit will be different. So, that you will see in the next slide. But before that I should discuss that there are certain overriding conditions or constraints. I already mentioned that what are the overriding conditions or constraints. The first constraint is that he is having maximum of rupees 50,000 to invest, and the second one, so this constraint is the investment constraint, and the second constraint is the storage space constraint, in which there is a place of maximum of 60 pieces, including both chairs and tables. So, these are the two constraints. Okay. Let us see how we can solve this problem. Okay. So, let me go to the next slide, dear students, and then let me explain. So, problem statement is again I have mentioned it here, so that you will get familiar with the problem statement. Now, for this problem statement, so let us take three different cases. The first case, suppose he decides to buy tables only. So, how many tables he can purchase? So, cost price of one table is rupees 2,500. And he is having 50,000 rupees to invest. So, the number of tables he can purchase is 50,000 divided by 2,500, which is 20, correct? 20 tables he can purchase. Now, if he purchase 20 tables and sell all these 20 tables, what will be the profit? Profit per table, per selling one table is rupees 250. So, selling the entire 20 tables, the profit will be rupees 250 into 20, that is rupees 5,000. Okay. So, in this case his profit will be 5,000. Now, let us take the second case. Suppose he decided to buy chairs only and no tables, only chairs. Okay. So, in 50,000 rupees, how many chairs he can purchase? So, we see the cost price of one chair is rupees 500. So, then by 50,000 rupees he can purchase 50,000 divided by 500, that is 100 chairs. So, he can purchase 100 chairs. But you see, dear students, there is a constraint, that 60 pieces. So, including chair and table, he can purchase maximum of 60 pieces because of the space constraint. Then what happened is that as there is a space constraint of 60 pieces, so what can be done? That he can only take 60 pieces. Therefore, he is forced to buy only 60 chairs. He is forced to buy only 60 chairs, right? So, what will be the profit? So, rupees 60 into 75, that is rupees 4,500. So rupees 4,500 will be the profit in this case, correct. Now let us take the third case. Okay, so in the third case what we see is that suppose he buy 10 tables and 50 chairs. Okay, so then in 10 tables and 50 chairs, what happens is that the profit from 10 tables will be 10 into 220 rupees 250, and from the 50 chairs it will be 50 into 75. So total profit will be 6,250. Okay, so in this case the profit will be rupees 6,250. So we see there are three different cases, and in these three different cases there are three different profits, correct. I hope you got it very clearly. Now one thing in the third case you need to check is that by purchasing 10 tables and 50 chairs, what will be the entire cost price. So 10 tables, so cost price of per table is 2,500. So entire cost price for tables will be 2,500 into 10, that is 25,000, and for 50 chairs it is 50 into 500, that is actually coming 25,000. Yeah, so it is total 50,000, 25,000 for chairs and 25,000 for tables. But in this case the profit is coming rupees 6,250. So we see there are three different profit margin for three different cases. Like this you can make many other cases. You can purchase some different number of tables and different number of chairs. So the problem comes is that what will be the optimal number of tables and chairs so that the profit can be maximum. So let me bring the next slide and explain it. Okay. So the point here is that what is the objective here? It will be here also I have mentioned the problem statement. So the problem statement here is that how should he invest his money in order to get maximum profit, and that is the most important question here. I repeat, how should the furniture dealer invest his money of rupees 50,000 in order to get maximum profit? Okay, to answer this question we need to formulate this problem mathematically. Let us see how to formulate this problem mathematically, and that I am going to discuss in the next slide. Okay. Just so here I have mentioned the problem statement in the left hand side, the same problem statement, so that you can refer to it. So let x be the number of tables and y be the number of chairs that the dealer buys. Then obviously the first constraint will be that x should be greater than equal to 0 and y should be greater than equal to 0. That is called non-negative constraint, because it is impossible to purchase negative number of chairs or negative number of tables. So that is called the non-negative constraint. It will be there always throughout all the problem we are going to discuss in the entire topic. The second one is that the dealer is constrained by the maximum amount he can invest is rupees 30,000 in this case. So the dealer is constrained by the maximum amount he can invest. Here it is rupees 50,000, and by maximum number of items he can store. Here it is 60. So now if he is purchasing x number of tables and y number of chairs, what is the cost price of one table? The cost price of one table is rupees 2,500. So cost price of x number of tables will be 2500 into x. Cost price of one chair is y. Sorry, cost price of one chair is rupees 500. Okay. So, cost price of y chair should be 500 into y. So, that is the entire cost price 2500 into x plus 500 into y. That cost price must be less than equal to 50,000, that is the investment constraint, right. So, now if we simplify this thing, if we take 500 common from both the sides of the inequality, it is coming as 5x plus y is less than equal to 100. So, that is the first inequation. And the second inequation is that x plus y should be less than equal to 60, because maximum number of chair and table, including chair and table, maximum number of items can be 60, that is the storage constraint. So, x plus y is less than equal to 60, that is the storage constraint. So, we have two constraints here, that is investment constraint and storage constraint, and before that we discussed about the non-negative constraints. So, but what is our objective? Our objective is to have the profit maximum. To have the profit maximum, what is the profit? By selling one table, by selling one table the profit is rupees 250. So, by selling x number of tables, the profit will be 250 plus x. In the similar manner, by selling one chair, the profit is rupees 75. So, by selling all the y chairs, the profit will be 75 into y. So, now by selling all the x chairs and x tables and y chairs, the profit amount will be 250 into x plus 75 into y. Our objective is to maximize that value, 250x plus 7 into y. So, our target will be to find the value of x and y in such a manner that 250x plus 75 into y is maximum, and that is our objective. That is why it is called objective function. So, what is our target? Our target is to maximize z. Z is the objective function. Maximize z, which is nothing but 250x plus 75 into y, subject to the three constraints. The first constraint is that 5x plus y less than equal to 100, that is the investment constraint. Second constraint is that x plus y less than equal to 60, that is storage constraint. And the third one is that, which is quite obvious, x is greater than equal to 0 and y is greater than equal to 0, that is the non-negative constraint. So, subject to all these three constraints, our target is to find the maximum value of 250x plus 75y, and that is the linear programming problem. I hope so far it is absolutely clear. Now, let me go to the next slide. So, let me repeat once more. The dealer wants to invest in such a way, so as to maximize the profit, say z, okay, which stated as a function of x and y given by z equal to 250x plus 75y, that is the objective function, subject to the constraint 5x plus y less than equal to 100, x plus y less than equal to 60, and x and y both are greater than equal to 0. So, what we see? We have to maximize the linear function z, that is the linear function z. It is a linear function of x and y, 250x plus 75y. It is a linear function, that is the linear objective function z. Subject to the certain condition determined by a set of linear inequalities. If you see, dear students, all these are linear inequalities with variables as non-negative, quite obvious. There are also some other problems where we have to minimize a linear function. So, in this case we are maximizing that objective function which is linear, but there could be some other problem. For example, the problem where we need to minimize the cost, or some other problem where we need to minimize the resources. So, in other problem, some other problems where we have to minimize a linear function subject to certain conditions determined by a set of linear inequalities which with variable as non-negative. Such problems are called linear programming problem. So, now it is clear why it is linear programming problem. Linear because of all these equations and inequations are linear. Programming means we need to have a certain kind of actions, that is why it is programming. And problems because we are solving a problem, that is why we are solving a particular problem, that is why it is a linear programming problem. So, what we are going to learn? We are going to learn how to solve linear programming problem, and that we are going to discuss in the next few slides. Okay. So, before I go for the solution to the problem, so let us discuss some terminologies here. So, and you already aware of it because I already explained few minutes back, but let me tell you once more. Thus, what we see, a linear programming problem is one that is concerned with the finding the optimal value. Optimal means it could be either maximum or minimum depending on the problem statement of a linear function called the objective function z of several variables. In this case it will be two variables x and y subject to the constraint conditions or constraint that the variables are non-negative and satisfy a set of linear inequalities called the linear constraints. The term linear applies that all the mathematical relations used in the problem are linear relations, be it an objective function or a non-negative constraint or a non-negative constraint or a linear constraint. So, that is why it is called a linear programming problem. Now, the term programming refers to the method of determining a particular program or plan of actions. That is why it is called linear programming problem. I hope it is clear the nomenclature, why this type of problem is called linear programming problem. I hope this is clear. Now, let me go to the next slide, dear students. Though I have mentioned earlier, but let me quickly summarize about the objective function, constraint and optimization problem. Okay. So, before we proceed further, okay, we now formally define. So, we are going to define formally, okay, some terms which we shall be using in the linear programming problem. The first one is called the objective function. What is the formal definition of an objective function? Objective function is a linear function z equal to ax plus by, where a and b are constants, which has to be maximized or minimized, is called a linear objective function. In the example what we are discussing about the selling of chair and table, the objective function is 250x plus 75y, that is the objective function. It is a linear objective function. Linear objective function. Now, variable x and y are called decision variables. So far we understood two things. The first one is the objective function and second thing is the decision variables. Now, dear students, let us go to the constraint. You already aware, but let me give the formal definition. The linear inequalities or equations or restrictions on the variables, I repeat, the linear inequalities or equations or restrictions on the variables of a linear programming problem are called constraints. So, in this case, x greater than equal to 0, y greater than equal to 0 are called non-negative constraints, and all the constraints I have mentioned earlier 1 to 4 are constants. So, these are the constraints. So, let me show you, let me take you to the previous slide and let me show you once more. So, these are the equations, you see, equation 1 to 4, this is equation 1, x greater than equal to 0, this is equation 2, y greater than equal to 0, this is equation 3, 5x, in equation actually, 5x plus y less than equal to 60, and this one, fourth one, x plus y less than equal to 60. So, these are the constraint. Okay. So, now go back to the let me come to from where I was discussing. Yeah. So, these are the constraint. Now, optimization problem. What is optimization problem, dear students? So, let us understand what is optimization problem. Optimization problem is a problem which seeks to maximize or minimize a linear function, say of two variables x and y, subject to certain constraints as determined by a set of linear inequalities, is called an optimization problem. Sometime in the board examination, these definitions also asked: what is objective function, what is constraint, what is optimization problem. So, you need to write exactly like this whatever I have said. Linear programming problem are special type of optimization problems. So, the problem of investing a given sum by the dealer in purchasing chairs and tables is an example of an optimization problem, okay, as well as of a linear programming problem. We shall now discuss how to find solutions to a linear programming problem, and in this chapter we will concern only with graphical method. So, we will see that how to solve a linear programming problem only leveraging graphical method. Okay. So, let me bring the next slide and then we will discuss. This slide is very important to understand the solution, the core of the solution. So, very important. So, please concentrate here. So far whatever we have discussed, we discussed about different terminologies and what is the linear programming problem, why it is called linear programming problem, why it is linear, why it is programming, why it is a problem, all these things. But let us now come to our end target, that how to find the solution of a linear programming problem. So, that is why it is mentioned graphical method of solving linear programming problems. So, just a quick recap. In class 11, we have learned how to graph a system of linear inequalities involving two variables x and y, and to find its solution graphically. Let us refer to the problem of investment in tables and chairs as discussed in the previous few slides. So, if you recall, what is the objective function? Objective function is to maximize the profit. It was 250 into x plus 75 into y. Now, what are the constraints? The first constraint is 5x plus y less than equal to 100, and that constraint is called the investment constraint. Second constraint is x plus y less than equal to 60, that is a space constraint. And then x greater than equal to 0 is a non-negative constraint, and y greater than equal to 0 is non-negative constraint. So, the graph of all these inequations, first let us put. First we are putting that 5x plus y less than equal to 100. 5x plus y is equal to 100 is this straight line. Let me mark this straight line in the red color. This is the straight line which represents that 5x plus y equal to 100. Now, what will be 5x plus y less than equal to 100? So all the left portion of this straight line, that will be the solution region, correct? Because we know an inequation is having infinite number of solutions, correct? This one. Second one, let me describe it in the green color, is that x plus y less than equal to 60. So first we need to seek x plus y equal to 60. So what is x plus y equal to 60? That is the line which I am drawing on the green color. It is already drawn in the black color in the material. So I, again I have drawn on top of it in the green color. Now here also x plus y is less than equal to 60. So that means the solution region will be the left hand side of x plus y less than equal to 60, correct? This is the class 11 knowledge. Okay. Now next condition is that x is greater than equal to 0. So let me do it in the blue color. X is greater than equal to 0, that means it will be this one. I'm so sorry. X is greater than equal to 0, that means it will be this region, correct? It will be this region. And y is greater than equal to 0 will be this region, correct? So our solution region will be which is common by all these four inequations, which is actually the blue shaded region, if you see, where all these lines actually intersected, overlapped. Okay. So now let me read out the statement which is there in the left hand side. The graph of this system, that is the shaded region, consists of the points common to all half planes determined by the inequalities 1 to 4. Each point in this region represents a feasible choice open to the dealer for investing in tables and chairs. That means what? If you see, so this is the solution region, okay, this shaded region. Now if you take a point here, the value of x and y could be a solution. The value of x represents the number of tables, and y represents the number of chairs. Okay, so that could be a solution. So any point in this shaded region could be a solution. These all are feasible choice. As all these choices are feasible choice, so that is why the region therefore is called the feasible region of the problem. Every point of this region is called a feasible solution to this problem. Thus we have feasible region, the common region determined by all constants including the non-negative constants x greater than equal to 0, y greater than equal to 0 of a linear programming problem is called a feasible region or solution region for the problem. So if you see in this case OABC, so that means which part is OABC? So if I mark properly, just a minute, let me mark in the red color. So this is O, this is A, this is B, and this is C. So I can say OABC, that is the feasible region. The region OABC is the feasible region for the problem. The region other than the feasible region is called infeasible region. Okay. Now what is feasible solution? The points within and on the boundary of the feasible region represent feasible solution to the feasible solution of the constant in the figure. So if you look into the figure, every point within and on the boundary of the feasible region OABC represent feasible solution to the problem. For example, if we take all these coordinates of the point O 0, 0, that is a feasible solution. Okay, then A, whose coordinates is 30, 20, 0, that is also a solution. That is the coordinates of the point A, 20, 0, that is a solution. If we see B, which is 10, 50, that is also a solution. Now if you see C 0, 60, that is also a solution. Any point outside the feasible region is called an infeasible region. Okay. So for example, 25, 40 is an infeasible solution of the problem. Means that is not a solution to the problem in simple terms. Okay. So I hope it is clear. Now let me go to the next slide to discuss further. Okay. Okay. The optimal or feasible solution. Okay. Any point in the feasible region, that gives the optimal value, that is either maximum value or minimum value, that depends on the problem. So any point in the feasible region that gives the optimal value, maximum or minimum of the objective function is called an optimal solution. Now we have seen earlier that the region OABC satisfies all the conditions 1 to 4, and since these are infinitely since there are infinitely many points, it is not evident how we should go about finding a point that gives a maximum value to the objective function, in this case 250x plus 75y. So I repeat once more. In the previous slide you saw that the region OABC, okay, if I can take you to that slide also once, that if you see in this one, that OABC, that region, that O, A, B, C, A, B, C, this region, any point is this region is a solution. So means in this region, if you find any point, it will have a x and y coordinates, that will be a solution. But the point is that, the question is that how we can make sure that those values of x and y are giving us the maximum value for the objective function z 250x plus 75y. So in this case it is a maximization, but in some other case, some other problem, if it is a problem related to cost, or if it is a problem related to usage of resources, it will be a minimization problem, but whatever it is an objective function. So in context to the present problem of the furniture dealer, so here we need to find the maximum value of 250x plus 75y. So the point is that for what value of x and y, that 250x plus 75y will be maximum. So that depends on the following two theorems. Okay, proof of this theorem is beyond the scope of our present study, so we are not going to discuss the proof, but we should definitely discuss the theorem, state the theorem. So what is the first one? Theorem 1 says that let R be the feasible region which is a convex polygon for a linear programming problem, and z equal to ax plus by be the objective function. Now before I proceed further, I would like to tell you what is a convex polygon. Convex polygon is something like this. Suppose this is a polygon. Convex polygon means is that if you take 2 points, okay, on this polygon, and if you join a line, the entire line will be in this polygon, that is called convex polygon. Now then, impossible, sir, is it possible to have kind of a polygon where if you take 2 points on that polygon, if I join a straight line, it is not on that polygon? Yeah, possible. That kind of polygon is called concave polygon. What is that? Well, let me give you one example. Suppose our let me draw it properly. Suppose this is a polygon. Okay. Now we take 2 points. Here 1 point and here 1 point. Now if I join a straight line, you see the portion of the straight line is going outside the polygon. So that is why this polygon is called concave polygon. So this polygon is called concave polygon, which is not our point of discussion. So we are discussing only with the convex polygon. Okay. So I repeat once more that let R be the feasible region, convex polygon for a linear programming problem, and let Z equal to Ax plus By be the objective function. When Z has an optimal value, maximum or minimum, where the variables x and y are subject to constraints described by the linear inequalities, this optimal value must occur as a corner point vertex of the feasible region. Okay, so those vertices will be the corner point. Okay, a corner point of a feasible region is a point in the region which are intersection of two boundary lines. Okay, so let me show you once more by going back to this one. So you see here, now this is one line and this is one line, they intersected here in this point. So this is one corner point. Similarly, this is one corner point, this is one corner point, and this is one corner point. Correct? So now let me come back to the point. Yeah. So let me repeat theorem on once more. Let R be the feasible region, which is a convex polygon geometrically, for a linear programming problem, and let Z equal to Ax plus By be the objective function. Then Z has an optimal value, maximum or minimum, where the variable x and y are subject to constraints described by the linear inequalities. This optimal value must occur at a corner point vertex of the feasible region. And as I said, a corner point of a feasible region is a point in the region which is the intersection of two boundary lines. That is the theorem 1. Now let us come to theorem 2. Theorem 2 tells that let R be the feasible region for a linear programming problem, and let Z equal to Ax plus By be the objective function. If R is bounded, then the objective function Z has both a maximum and minimum value on R, and each of these occurs at a corner point vertex of R. A feasible region of a system of linear inequalities is said to be bounded if it can be enclosed within a circle. Very important to understand. Suppose we get so if I give an example here, suppose these are the coordinate axes. So this is origin, this is positive direction of x axis, this is positive direction of y axis. We are not considering the negative direction because that is not our discussion. Suppose here we get a feasible region which is a kind of a convex polygon. So suppose we get this one. Suppose this is our feasible region, that is a convex polygon. Now in this statement, so a feasible region of a system of linear inequalities is said to be bounded if it can be enclosed within a circle. That means what? We can enclose this entire bounded region, feasible region, within a circle. Then it is called a bounded one. Otherwise, it is called unbounded. So what is unbounded? Let me show you. Okay. Suppose we have a solution something like this, and it is something like this. So you cannot cover that entire feasible region within a circle. If you construct a circle something like this, then this region is also within this one, because this line can be extended further. So this portion is actually outside this circle. So that is why it is mentioned here. Unbounded means that the feasible region does extend indefinitely in any direction. So in this case it is actually being extended in this direction. Okay. So that is unbounded. Now here is a remark. What is the remark? If R is unbounded, if the feasible region is unbounded, okay, then a maximum or a minimum value of the objective function may not exist. However, if it exists, it must be at a corner point on R, so which is described in the theorem, first theorem. So that means it could be either this corner point or this corner point, in case maximum or minimum value exists. So these are the two theorems. Now in the next class we will discuss about all these things in details, but before we conclude, let me show you the solution to this linear programming problem we started discussing with today. That is the problem with the of the furniture dealer. Okay, so let me discuss this solution. Now, if you look into this feasible region is this one, that covered by the region OABC. So the OA, P and C. Coordinate of the point O is 0, 0. Coordinate of the point A is 20, 0. Coordinate of the point B is 10, 50, and coordinate of the point C is 0, 60. So as it is mentioned here. Okay, OABC are having the coordinates 0, 0, 20, 0, 10, 50 and 0, 60 respectively. Let us now compute the value of z, the objective function. What is the value of z? It is let me bring the function z. I think it is 250x plus 75y. Yeah, 250x plus 75y. So here the value of z, what we are computing is that z is equal to 250 into x plus 75 into y. So for when x equal to 0 and y equal to 0, the value of z, that is 250x plus 75y, is actually 0 because both are 0. When x equal to 0 and y equal to 60, the value of z, that is 250x plus 75y, that is actually nothing but 250 into 0 plus 75 into 60, that become 4500. When x is equal to 10 and y is equal to 50, in that case the value of z, that is 250x plus 75y, become 250 into 10 plus 75 into 50, that becomes 6250. And when x is equal to 20 and y is equal to 0, we get the value of z, that is 250x plus 75y, as 250 into 20 plus 75 into 0, that is 5000. Among all these four values, we see that 6250 is the maximum value. So we observe that the maximum profit of the dealer result from the investment strategy 10, 50, that is by buying 10 tables and 50 chairs. This method of solving linear programming problem is referred as corner point method, and this corner point method and relevant problem we will be discussing in the next session. So with this note, let me conclude the class for today. In case you have any question, please ask me. In case you do not have any questions, let us conclude. Thank you.
Thank you, sir.